This PDP-1144 is very cool, but you know what would make it even cooler? If it was a supercomputer. Impossible, you say? Well, not if we bolt a floating point systems FPS 100 array processor to it. We can get a full 8 megaflops of processing performance out of hardware from the late 1970s, which is absolutely epic. But there's if we can pull it off. I don't know if we can pull it off, but we're gonna give it a shot at the very least. Today's episode is actually about a hard drive, and you know, if you want to go check that out now, there's like timestamps below with chapter titles or whatever. But I'm not going to pass up an opportunity to talk about floating point systems because I'm just absolutely in love with this company. Initially, all I had was a collection of about 8 boards, these 8 right here, and that was it. And then I got my hands on an FPS 3000, which was really epic. But we discovered that the FPS 3000 is an XP32 ynnuB, or multi-instruction multiple data, add-on for an FPS 100. So we still need the FPS 100 to act as a control processor for the FPS 3000. So we're right back to where we were in that we need a functioning FPS 100, and all we got are a couple of boards. Only clearly I don't have just a couple of boards. I got in touch with a company called JM Trading, and Mary helped me a ton. They had a massive number of FPS boards, and we managed to get them sent down here. You can see this box is full of FPS boards. It's about an even split. About half of the boards are FPS 100, and the other half are AP120B boards. The AP120B is kind of the predecessor to the FPS 100, and it was all 7400 series, discrete logic, and it was actually a little faster. It could pull off about 12 megaflops, but I do have a complete set of FPS 100 boards, and anything that I was missing with my original 8 here has now been filled out with the extra ones that we got from JM Trading. But ultimately, we don't have a backplane for any of this, and the backplane is like a custom wire-wrapped nightmare. So I have to figure out the pinout of the PDP-11 interface card so that I can build a backplane from scratch and then plug all the individual cards into it and then get that plugged into the PDP-11. But the PDP-11 is also kind of incomplete at the moment. Now, the FPS 100 gives us 8 megaflops of performance, which doesn't really sound like that much today, but in the late 1970s, this was enough performance to make Cray start to sweat a little bit. By the time we got to the mid-1980s, floating point systems had introduced the XP32 ynnuB processor, or multiple instruction, multiple data processor, and depending on how many of these XP32s you bolted to your FPS 100, you could push megaflops performance up to over 100. This was enough raw performance, raw supercomputing performance, that Cray just bought floating point systems. They just outright bought the company. That's how epic floating point systems was. But even if I did have a fully working FPS 100 to slot into this cabinet, it couldn't really do much of anything because the PDP-1144 here is like literally just a CPU and a little bit of memory, and that's it. There's nothing else. The 2 floppy drives here are not connected up to it because they need to be restored, and I need to get some kind of hard drive going on in this thing. And that drive is this one. This is a Priam, or a Priam 15450, and man, I should have memorized my notes. I'm terrible at this game. It's like a 2-platter hard drive. Each of the platters are 14 inches. I think it's 160 megabytes. It's also a little too new for this room. I have a rule that I try to follow, which is nothing newer than 1984. And I believe this hard drive was built in 1985. But, I mean, come on, it's a 14-inch hard drive. This is so unbelievably cool. I gotta bend the rule just a little bit so I can work on this thing. But while I do think it's gonna be perfect for our PDP-11 here, it has some pretty serious problems. If I spin it around here, on this side here, we have our interface board here, which is totally fine. And then we have our analog board here, which is very much so not fine. Something bounced into it or fell into it and broke a ton of components. We have transistors that have completely rusted into oblivion, but the bigger problem is that we have these resistor packs that have also been smashed. Normally you see a resistor pack like this and you think it's dead simple. It's just a collection of resistors with one side all commonly tied together to create a pull up or a pull down. And for like 9 of the bad resistor packs on here, that's exactly what they are. They're 470 ohm pulled downs to -5 volts. However, for 5 of the resistor packs that are smashed, and many more that aren't smashed, they aren't that. They're far more complex. And thankfully we have the schematics for this Priam drive, and I was able to figure out what those resistor packs look like, and it's this. If we look at resistor pack 52 here, this is the most egregious example. We have 10 pins and all sorts of wild interconnections with very strange resistor values. It's like, all right. I know that there's just going to be absolutely no way that I'm going to find replacement resistor packs with this exact layout, with this exact resistor values in it. It's not going to happen. So what I'm going to have to do is rebuild this resistor pack from scratch in a SIP form that I can then slot in. It's going to look a little Frankenstein on here, but I have a full list of everything that's gone bad here. It's about 10 or so transistors, and then we've got about 15 of these resistor packs, and I think we have 1 capacitor that's gone bad. And if we get all of that replaced, I think I'll be okay with putting some power in this thing and hopefully seeing it spin up today. But even that is not easy because the power supply is not included with this thing. That was a separate piece that I didn't receive when I got this drive. So we're gonna have to build a power supply that gives us 24 volts at 7 amps, 5 volts at 4 amps, -5 volts at 2 amps, and -12 volts at 0.7 amps. So we got a lot of work ahead of us today, but I think the first topmost priority is going to be getting to work replacing all the smashed components, and I have a big old order from Mauser here, so let's get to work. To get both boards out, there are 10 screws around the periphery that lock them down to the frame. As much as I hate slotted screws, these mercifully came out with ease. Next, we have to disconnect the HDA from the analog board, and that connection is via these 4 IC style plugs. These are what carry all the data to and from the disk, as well as the control signals to seek the heads. Finally, we can remove the analog board, being careful not to bend up the IC style plugs as they slip through the opening in the PCB. The interface board then lifts up and out, although it's important to note I'd already disconnected the power connector a long time ago. This foam filter material here is starting to degrade and probably is causing more harm than good. In order to get it out, I need to peel off this, I don't know what it is, but it's sticky and kind of gross. All right, we're making good progress here. Let's flip this thing on its side and take a look at the spindle motor controller. This PCB wasn't hit by anything and looks to be in pretty decent shape. So I think I'll leave it where it is for now, and instead move attention over to the SMD interface board. At the heart of this board is an Intel P8035, which is an 8-bit microcontroller that features 96 instructions, 27 I/O lines, and 64 bytes of internal RAM. There isn't any onboard ROM though, which means if we look back at the SMD interface board, yep, there we have a little EEPROM that contains all the code to run the interface. We also have this little Intel P8253 IC over here, which is a programmable interval timer. I don't know enough about hard drive interface design to know exactly what this thing does, but I do know that right behind this little IC is a 74LS244 that has seen better days. It definitely took a hit, so let's get it replaced, which means the trusty Radio Shack desoldering iron comes out again. Look at this thing just completely empty each through hole. To get the IC out, I just pry gently back and forth on it and it comes out with ease. But a new socket goes in and then the replacement IC gets pushed into that. Now this is a 74LS245, but that should be pin compatible. With the interface board taken care of, let's shift over to the atrocious analog board. Interestingly, it also has a D8035 microcontroller and code storage ROM. Only this 8035 is made by NEC. Right below the microcontroller is an Intel P8243, which is an I/O expander specifically for the 8035. This, I suppose, gives it enough I/O to handle the tricky analog nature of controlling a hard drive. But the real reason we're here is to fix these decimated components. Things are cracked and broken and all bent out of shape. The worst are these transistors that have rusted completely out. Let's start with the easy stuff though, like bending this power resistor back into shape so it doesn't short out on something. And the bent fin on this IC heatsink will drive me mad if I don't do something about it right now. Fortunately, it bent back into shape without cracking or breaking. Then it's time to really put the Radio Shack desoldering iron to the test. First, I went through and added fresh solder to the nearly 150 connections that I have to get completely free of solder. The new solder mixes with the old stuff and makes it much more amenable to flowing, making it a lot easier to desolder. Even after thoroughly desoldering every pin I could, nothing really wanted to budge on the top side. It took several back and forths between the backside and front side, just trying to get the components to break free so I could put some pressure on them and get them removed. The transistors were actually easy peasy to get out. The desoldering iron made quick work of the connections and then they just popped right out. The SIP resistor packs put up much more of a fight. But eventually I got everything removed, and looking closer at the board, it's absolutely disgusting. Lots of corrosion all over the place. So let's pop the CPU and ROM out for safekeeping. Then I'm going to give this thing a proper wash, starting with some simple green and a plastic bristle brush. After some very thorough scrubbing, I'll take it over to the sink and rinse it off completely. Then, to accelerate the drying process, I'll use the air hose to get the bulk of the water out, particularly from under the ICs. But don't worry, this thing won't see power for another 2 days yet. With it clean, let's start trying to build out one of our resistor packs. There's no schematic for how these 470 ohm pull downs are wired specifically, so I'm taking a bit of an educated guess here, and honestly, I hate how this turned out. But I'll get another chance to redo these in the future because I made some discoveries while doing this. All right, two things. First, this episode almost didn't happen. I filmed the intro where I talked about and introduced the PDP-11 and the FPS 100 and all that stuff. And then I discovered Taskmaster on YouTube, which is particularly the season with Javie Martzoukas, and just subsequently lost 2 days of my life right there. But I have finished that season, so we're back into it, and leads me up into the second problem, which is that we have a discrepancy between the schematics and the actual board. The schematics are for revision 200214, and I happen to have revision 200515. And some things are in different places. Notably, a lot of the resistor packs are in different places. But man, 10, 11, 12, 13, 14, then 46, 47, 50, and 52 are all different from this board to the schematics. So, man, I'm not sure the best way to tackle this. I think, gonna sit down and beep out where each pin of the resistor pack goes and find out what ICs or what other components they're connected to, and see if I can find the similar or same location within the schematic, because the numbers might be different, but the design might be the same. And if I can do that, then I can figure out what kind of resistor pack it is and how to construct it. All right, that took a couple of hours, but I think I've mostly figured it out. It's like what a nightmare, man. All right, so resistor pack 10 on my PCB seems to match resistor pack 16 in the schematics. 11 matches 17, 14 matches 21, 12 and I believe 13 match 19, 46 matches 58, 47 is a unique one, 52 matches 65, and 50 matches 64. Man, this is what... All right, well, just keep working on it, I guess. Yep, you guessed it. I got the layout of these simple pull-down packs wrong. Turns out pin 1 is ground and pin 8 is -5 volts. So my common needs to go over to pin 8, which requires removing the resistor I erroneously installed there. That looks much better, but we're still not there yet. Pin 1 is supposed to do something. Turns out there's 10 nanofarad of capacitance between pin 1 and pin 8. These things have an internal decoupling capacitor. And keep in mind, these are the simple packs. Anyways, there we go. Resistors in place, common in the right pin, and decoupling cap added. It doesn't actually look that bad, but don't worry, it gets so much worse from here. Look at how complex these packs are in comparison. I tried to lay out the resistors in as logical of an orientation as I could, but I have one more massive problem. Because I placed my Mauser order for different resistor packs, I'm missing a lot of the weird, unique resistor values. So I had to recreate those values using more standard values in parallel. Let me be clear. I hate this. I hate this with every fiber of my being. It was tedious, extremely difficult, and even without parallel resistors, it still would have been a nightmare. I didn't even film me making these abominations of resistor packs because it was just so not fun. But I got there in the end. It looks like a steampunk eldritch horror, like some city planner wanted pockets of chaos and terror that only Carl Urban as mean mug and Judge Dredd could police.
If you do not comply, the sentence is death.
But it should get the job done. If this works, I'll probably go through someday and remove this nightmare fuel and replace it with SMD-based PCBs that are much cleaner and more reliable. But for now, this should get us to the next step, which is going to be figuring out how to get electrons into this thing. Initially, it had an optional power supply that I didn't receive, but it just uses plus 24 volt, plus 5 volt, minus 5 volt, and minus 12 volts, which I will recreate using Meanwell's supplies. I think the power supply is meant to be external to the drive, but Meanwell's are so compact, I think I can squeeze it inside of the cage. After removing the HDA and setting it aside, I'll lay out the Meanwell supplies roughly where I want them to live. That should clear the HDA perfectly, but before I get too carried away, I need to clean the metal off. It's a bit corroded. A Scotch-Brite scrubby makes quick work of it, and now I can set my Meanwells in place without getting gross. I'll mark them out with a Sharpie for where I want them to be permanently, then I'll break out the drill and start punching holes in metal. With all the mounting holes drilled out, I'll screw the supplies into place with the appropriate hardware. And there we go, all mounted up. That's gonna work like gangbusters, I think. Now I just gotta wire it. But I'll be honest with you, I absolutely love doing this. Wiring up Meanwell power supplies is one of my all-time favorite things to do. It's just so wonderfully cathartic. I even had the appropriate power plug, so I just need to crimp and insert the pins. And look at that. Everything wired up neat and tidy. What a stark difference from the catastrophe of the resistor packs. Let's double check that I've got it pinned out and wired up correctly. 5 volts is good, minus 5 volts looks good too, minus 12 volts is in the right place, and finally, plus 24 volts is looking spot on. Let's get the HDA back into place. It's a little fiddly, but not because of the Meanwells. They're super out of the way. Once in place, there are 4 screws that go into rubber isolators, and that's it. Then let's get the interface board and the analog boards back into place. And there we go. Everything is fully installed. Just look at those Meanwells. They sit in there flawlessly. That makes me feel way better after the resistor pack fiasco. The final step is to unlock the heads and spindle by flipping this lever here. All back together, I think we're ready to throw some electrons at it. Well, the first things first, let's remind ourselves that this thing was effectively scrapped. There had been enough damage to it that even I was skeptical it could ever be brought back, but we've given it a solid go. And we have a proper power supply in it. Everything else looks to be pretty clean, so if it doesn't catch fire, I'll consider that to be a victory, but we're really hoping to hear it spin up. So fingers crossed, knocking on wood, praying to all the computer gods. Here we go, flipping the switch. Well, it didn't go up in smoke, but nothing else happened. Oh, man. All right, let's try again. Make sure at least that we're getting 5 volts up to the right places. I'm on the pin of the 74LS244 that I replaced. So I'll go ahead and flip the power switch here. We do have 5 volts there, but again, totally inert. Absolutely nothing at all happening. Completely dead. All right, let's check the full voltages over here. Make sure that we're getting everything. Pin 2 is 24 volts, that is correct. Pin 3 here is negative 12 volts, that looks good. Negative 5 volts, plus 5 volts. That's voltages going to where they should be. The lack of spinny has nothing to do with the analog or the interface board on top. It has everything to do with the power board on bottom. That should be causing the spindle to spin up immediately, and well, as we can hear, nothing's happening, but something is actually happening. Right now we're looking at the fan of the spindle here, and if I flip the power on, watch this. It tried. It tried its best. It didn't get anywhere though. Well, the one board that we didn't look at today is the one that is letting us down. That is this board right here, and there is no connection between this board and the analog or interface board up top. So as soon as 24 volts comes rushing in, this board should start sending power to the spindle to get the motor spinning and get the discs up to speed. But as we can see, it gives just 1/10 of a rotation and then stalls, doesn't go anywhere from there. So we'll give it one more try here. I've got it on a switch down here, you know, because it's the end of the day, and let's see if we can break something. So I'll go ahead and flip the switch. I didn't even get 1/10 of a rotation that time. But at any rate, that's what we're gonna figure out in the next episode. We'll dig into this board down here and see why it is not spinning our disc. And then if we can get the disc to spin, well, who knows? Maybe we'll figure out if this hilarious repair that we did to the analog board up here actually worked. So I want to thank you all so much for watching, and I hope to see you in the next one.